Okay, welcome back. We're in chapter 17. We're going to cover 17.1 and 17.2 in this video. So here we go. Chapter 17 is the physics of hearing, and 17.1 is titled sound. So sound is a physical phenomenon defined as a disturbance of matter that is transmitted from its source outward as a wave. So it is physical, which I just spelled wrong, physical, and it's just an oscillation of something, some object, something that's in space, and that disturbance, propagates outward. We have two kind of motions of concern. It is the rarefaction and compression. So if this is, say, a string that is being vibrated, a guitar string, whatnot, as it moves to the right, it's going to compress. It's going to push air together, compress it, and that will cause a kind of a thick, I don't know, it'll cause what we call the compression, and then on the other side of it, when it moves away, it creates kind of a lower pressure, a void, and that is called rarefaction. Then as the string moves back the other way, I don't know why this always has to move, it drives me crazy, but it moves the other way and we get a compression on the other side. So we get this now compression that was on the right hand side is now on the left hand side, and then this rarefaction that was on the left hand side is now on the right hand side. And so we get this kind of motion out of this that looks like this, right? The waves go out. That's not helpful. Where's my pen? So these waves go out. There's maybe a compression. There's another compression. You might get the next compression, and so on and so on. And these things just propagate outward away from the wave. As we do that, you might be able to see if I can get this all in one go. I think I sort of got it. There we go. So the freaking pen. I guess in this graph, the dotted line would be the rarefactions. These rarefactions right here correspond to that minimum. You got this bigger compression part is the maximum, but this essentially goes out as a sine wave in terms of pressure. And then this wave comes and enters your ear canal. Those waves of pressure hit the eardrum, which is it has some surface area that is then sensitive to these, vibrates, and then the ear converts the vibrations and the differences in these pressures into nerve impulses, which are then interpreted by your brain as sound, and then we hear them. So 17.2 is the speed of sound. 17 was rather short, but that's it. So 72, speed of sound. You hear or you see lightning soon, much quicker than you would hear it, right? The thunder comes usually a couple seconds after lightning, or depending on how far away it is, several seconds. But that's an indication that sound and light don't travel at the same speed. There's some sort of difference there. And it's kind of a large difference. If it were small difference, you probably wouldn't really notice so much. But you can, notice things like if you're in a stadium, far away up in the nosebleed, something might happen, and then you'll hear it happen a few seconds later. It's kind of an interesting little phenomena to see. I think Deer Valley does the overture of 1812, where they bring in real cannons to finish off the song at the very end, if you're familiar with that. And you can see the burst from the cannons, and you're usually far enough away that you see the burst, and it's maybe a half a second or a full second later that you hear the cannons go off. And so it's kind of an interesting little delay. If you're not expecting it, seems like you're kind of glitching in the matrix, kind of a deal. But they do indeed have a much slower speed. Than waves of sound have a much slower speed than light. But what happens is, say, like when a string vibrates, that's a string, I promise. When that vibrates, that's a bad string. I don't know. Here's a string as it vibrates, say, to the left, and then I don't know why I try. As the string vibrates, it's going to create these compressions and rarefactions, and these things are essentially just going to go out in, if we just look at it in going one-dimensional here, goes out in that direction. But this is just airwaves pushing into each other, slamming into the next airwave, slamming into the next airwave, and slamming into the next airwave. So it's just energy that gets transferred from wherever that sound source is being originated outwards, right? This if we have, say, compressions or rarefactions that are very far apart, that's going to be a very large wavelength and a very low frequency. Versus if I have, so like large lambda, low frequency, right? But if I've got ones that are super tightly compact, we're going to have a very small lambda. And that lambda, again, is just the distance. It's the wavelength. So it's the distance between a maximum and the next maximum. But if I have a small lambda, then I would have a very high frequency. And we can hear that. The difference between frequency is, high pitch frequency, some piccolo, some, I don't know, some I mean, you know what a high pitch is, versus something low. You can make it with your voice, right? Every time, like I teach, I have to change the frequency of my voice because my natural speaking voice doesn't carry through a classroom, and so I have to use this wah wah wah. Sounds nasally to me. It's weird, but this is how I have to speak to you. Otherwise, I would sound like this, and nobody can hear this, right? And so there's a high frequency that I have to use to speak to you in the classroom. And when I'm just sitting on my couch, this is how I talk. It's gravelly, it's weird, and this is how my voice is. So I can change that. I can talk like this. That's a higher frequency. We can tell these frequencies apart. The velocity of these waves, will have these waves propagating, but they also move with some velocity through that air or whatever they're traveling through, right? Sometimes sound goes through the air, sometimes it travels through solids, sometimes it travels through liquids. But the velocity here is equal to the frequency of that wave multiplied by its wavelength, right? But this velocity is usually a given, depending on what material. So this velocity depends mostly on the medium. Right? If it's air, it depends on what exactly is in the air. Typically, we would talk about our atmosphere. but it also depends on the temperature of that air. And there's other factors in it, but if you know that velocity, if you know the frequency, you can figure out the wavelength, or vice versa. But also, if you know frequency and wavelength of a wave, you can also then turn that around and figure out the velocity. There is a table of velocities in your book somewhere. I'm not going to be able to get it all in one clip here, but I can throw it into two. So here's the velocity of sound through some things. You can see there's a pretty big, if I can get these on one page, there's a pretty big difference, or a pretty big spread, really. This sizing drives me nuts. Here we are. We have air. Typically, and we'll talk about air. This isn't always the same value, but usually around 331 meters per second. That's what I speak to you at in the classroom. But through ethanol, it's significantly higher. When you get through solids, right, steel is really high, as is glass. But water, where is it? It's significantly higher than air. So typically, the more dense a material is, the greater the velocity of sound through it. But that's not the only factor. You can see down here, vulcanized rubber. Not that that's particularly hard, but it's dense. But it's, I don't know what to say, goopy, not goopy, but like, I don't know, rubbery. And whatever word I'm looking for here, it's not going to be a great transmitter of sound, and so it actually goes rather slow through this vulcanized rubber. But these are all typical speeds for, in this case, gases are at 0%. We'll talk about what happens when the temperature changes. These liquids at 20 degrees, I think I just said percent, 0 degrees centigrade. The liquids at 20 degrees centigrade, and then these solids don't. The difference is less significant in the solids, so we don't really care so much. But the velocity of a wave in air is equal to this base number, this 331 meters per second. But we can multiply that by the square root of the temperature in Kelvin divided by that temperature of 0 degrees, but also in Kelvin, so that's over 273 K. So the K should cancel out because the temperature should be temperature in degrees Kelvin, but it's the square root of the ratio of whatever temperature it is to, the freezing to temperature. That means if it's colder, right, this is going to not work out to the advantage of the sound. It's going to be a smaller number than 1 under that square root, so it'll actually slow the sound waves down. Whereas if it's super hot, it's going to then increase those the velocity of those waves. It is also noted that the velocity of sound and gas is related to the average speed of the particles in the gas, and that is they call it the RMS. That means root mean square. That means if you take the velocity of every single molecule of gas, square its value, add them all together, and then take the square root and add those and divide it. So it's if you've taken chemistry, you've done that. But the RMS is as 3 kT, and that T is temperature in Kelvin, divided by M, all under the square root, where K is the Boltzmann constant, and is equal to 1.38 times 10 to the negative 23 joules over Kelvin. And m is the mass of the particle. So if we're talking about oxygen, the average mass of, we have O2, we have CO2, so we would take the mass of whatever the average mass of those guys. So the mass of the particle, the atom or the molecules. And so doing so, we end up with, at 0 degrees, the velocity of sound in air is 331 meters per second. But at something like, say, 20 degrees Celsius, the velocity of that sound in that air is 343. So not a huge difference, but, you know, different. But you can do these calculations for any temperature now. If we have this, what are the wavelengths of audible sounds? Calculate the wavelengths of sounds at the extremes of the audible range between 20 and 20,000 hertz in 30 degree Celsius air, and assume the frequency values are accurate to 2 significant figures. Right? So we have, get a pen out, the velocity of the wave is frequency multiplied by lambda. But I've also got this velocity of the wave is for air, in air is 331 meters per second multiplied by that square root of t over 273. Okay. Now I'm going to use this second equation and calculate the velocity for 30 degrees. So I need that in Kelvin. So I'm going to add 273. That's 303 Kelvin. And so this is 331 meters per second multiplied by the square root of 303K over 273K. The K's cancel out, and my velocity ends up being 348.7 meters per second. So then the lambda, I can divide by f, so lambda is that velocity over frequency, and I can do this for 2. My maximum lambda is going to happen at the smallest value of f, because a smaller value of f in this denominator is going to make a larger value of lambda. And so that is the velocity of 348.7 meters per second divided by that frequency, so the 20 hertz. The hertz is 1 per second, so 1 per second cancels with the second in the denominator here, and I get meters, which is what we're looking for. And this ends up being 17 meters to 2 sig figs. And then likewise, my lambda minimum is going to be that same 348.7 meters per second over 20,000 hertz. And that ends up being 1.7 centimeters. Anyway, that's it. Kind of a short couple of chapters. Hopefully you guys have a good Thanksgiving. Enjoy your week, your time off. And then I'll see you guys on Monday. Thanks. Bye.